compared with other ways of treating the sample, you get completely different diurnal behavior in water. So their recommendation is cover the leaf with saran wrap, moist cheesecloth, or humidified plastic bag at least to try to minimize that water. Here's another experiment, this is a group of experiments that show the same thing. Errors arising from rapid water loss and measurable leaf water potential. Okay, so they compared, this was figure 2 here at the top, sorghum grown in a greenhouse, and they compared the uncovered water potential with the covered leaf water potential, and covered with a plastic sheath. So somehow a flat plastic thing that they put over the leaf, right? And here are the water potentials, 0, -1, -2 megapascals, and you can see that when the total water potential is close to, or as the total water potentials become more negative, it doesn't really matter if you cover the leaf or not. But there's a wide range here where if you don't cover the leaf compared to the covered leaf, you're going to get a more negative reading. All right. They repeated, this is with sorghum, so they repeated it with all these other plants, sunflower, what's this, maize, some other plants, cotton, sorghum. And they repeated this and saw similar behavior, although the exact the numbers vary with different species. Here's jojoba, that one, that's really adapted to xeric environments. And here these water potentials go down to -4 megapascals. You can see that for any of the species, as the water potential becomes more negative, these lines come together again. And it doesn't matter if you cover the leaf or not. Why is that? They reasoned that, it's because of the transpiration rate when you cut the leaf off the plant. And if you have your plant growing in conditions where it's really dry and it's water stressed, the stomata will be closed on that leaf. And when you cut it off the plant, the stomata are already closed and it's not transpiring very much anyway. And so that's why it doesn't matter if you cover it or not, if the water potentials are negative enough. They plotted this error, what they call the error, the difference between these two lines, as a function of the transpiration rate in this graph. And you can see that for all these species, as the transpiration rate went to 0, this error also went to 0. So again, their recommendation, cover your leaf up with a plastic sheet or some sort of a plastic. And again, it was similar to the last one where they lost an appreciable fraction of a megapascal within 30 seconds. They did not cover it. All right. So that's and for all these recommendations, cover the leaf up with plastic and keep it covered even when it's in the chamber when you're increasing the pressure, because the leaf can still lose water while you're fiddling around with the pressure here and trying to reach the end point. It can still be losing water. And that's especially the case if you increase the pressure rapidly. I don't know how familiar you are with working with compressed gases, but if I had a big T cylinder here, if I had this hooked up, right, to a big cylinder of gas, one of those big steel tanks that you see. If I had this hooked up and I opened the regulator here and let that pressurized gas fill this chamber, what happens with temperature in this system as I'm doing that? Typically, when you come from high pressure to low pressure, you decrease the temperature of the gas here. When you go from low pressure to higher pressure in this chamber, you increase the temperature here. So by taking this compressed gas here and making it not quite so compressed here, you transfer heat from this point to this point. And this increase in temperature here on this end can be appreciable. I don't know if you've worked with compressed gases, but if you have a big tank and open the valve on and leave your hand on it, you can actually freeze your hand to the top of the tank because it gets so cold from relieving that pressure. It's one of the things you have to be careful. All right, well, these people set out to have a look at that in the Agronomy Journal. Right? Changes in water potential during pressure bomb measurements. See, there's that bomb term, but that's 1978. All right. The problem with heating up the air in this chamber while you're making a measurement is the saturation vapor pressure of the air is a very strong function of the air temperature. What they did was, I forget what plant they're using. It doesn't matter. Yeah, it doesn't matter. What they did was they made pressure chamber measurements, but they put thermocouples all over their leaf and all over inside the chamber and in the air and all this to measure temperatures while they were increasing the pressure and while they were trying to come to the end point. And you can see, here's the air temperature. Let's just, they did it humidified and dried and covered and uncovered, and let's not worry about that too much. In all the cases, as they increased the pressure in their chamber, the temperature increased. So here, 40 degrees C, if they increased the pressure in the chamber at a rate of 0.53 bars per second. That's pretty fast. And as they reduced that rate of increase of pressure, they didn't get quite as big of an increase in temperature, but still, in all cases, the temperature increased. The water potential, they found, can change by 1/10 of a megapascal while you're making the reading itself. So this is where that recommendation of increasing the pressure slowly comes from. And also it helped to cover the leaf up somehow with a plastic or humidified plastic bag. Here's just a summary table of the errors that they had in the system. Right? Remember, this is a good time to remember that the transpiration rate of the leaf, the rate of water loss from a leaf, anywhere inside the chamber or out in the field growing in the sunlight, the transpiration rate is approximately equal to the total leaf conductance for water vapor, and we'll get into what that means later, times the driving force for that movement of water, that transpiration of water, which is the partial pressure of water vapor inside the leaf minus the partial pressure of water vapor in the air outside the leaf. The partial pressure of water vapor in the leaf, in the air spaces inside the leaf, is usually assumed to be the saturation vapor pressure at the leaf temperature. Here's a table of saturation vapor pressure. That's what this E0 T leaf means. Saturation vapor pressure as a function of temperature. You can see this blue line really increases a lot as the temperature increases. So as the temperature of the leaf increases, this difference gets bigger and bigger and bigger. And with a constant leaf conductance, the leaf loses more and more and more water. So it's important not to let the leaf heat up very much while you're making the measurement. Otherwise, you're going to lose water faster. And when you lose water, you change the water potential. This is a useful equation. It's got an analogous equation for CO2 flux. So this is water vapor flux, right? Water vapor leaving the leaf. It's got an analogous equation for net CO2 assimilation, which is leaf conductance for CO2 times the difference in CO2 concentration inside the leaf and in the atmosphere. So here's the driving force for CO2 diffusion into the leaf is because higher concentration outside the leaf, lower concentration inside the leaf. CO2 diffuses from high concentration to low concentration. The conductance of the leaf is this factor that relates the two. Bigger difference in CO2 concentration, higher photosynthetic rate for constant leaf conductance. This is, it's an Ohm's law analogy, right? It's the same as Ohm's law. This is a reason, getting off subject a little bit, this is one of the reasons why C4 plants are more water use efficient than C3 plants. If the transpiration rate is the total leaf conductance for water vapor times the saturation vapor pressure at the leaf temperature minus the vapor pressure of the air divided by the total pressure. This is sometimes called the difference in the mole fraction of water vapor inside and outside the leaf. So for a C4 plant, the CA is the ambient CO2 concentration. CI is the CO2 concentration of the air spaces inside the leaf. For a typical C3 plant, CI is maybe on a CA of 400 parts per million. CI may be 250 parts per million. But for a C3 plant, but for a C4 plant, CI may be 120 parts per million. So at equal conductances, the C4 plant will have higher photosynthetic rate compared to a C3 plant. Another way to look at it is, for equal photosynthetic rates, the C4 plant can have a lower conductance. That lower conductance for CO2 is related to a lower conductance for water vapor. And so that lower conductance means the C4 leaf loses less water for a given photosynthetic rate compared to a C3 plant. Hence, greater water use efficiency in C4 compared to C3. What are the reasons for all that? Well, there's reasons. Remember photosynthesis? So the C4 photosynthesis, the initial step of carbon fixation is to fix CO2 by PET carboxylase into a 4-carbon compound. That happens in the mesophil cells. That 4-carbon compound is transported to the bundle sheath cells where it's decarboxylated, CO2 comes back out, and then it's fixed by Rubisco, the enzyme called Rubisco, into Calvin cycle and normal photosynthesis. It turns out that Rubisco, that enzyme that catalyzes the initial step in C3 photosynthesis, also, if CO2 doesn't come along to bind with RUBP, it'll fix oxygen with RUBP. So oxygen is a competitive inhibitor of carboxylation process for Rubisco. C4 plant avoids that because PET carboxylase doesn't fix O2. Doesn't matter what the O2 concentration is. So it can, and for C3, again, this is way off topic, but for C3, this fixation of O2 with RUBP ultimately results in half of a CO2 molecule being produced. So every 2 oxygenations, you get a CO2 out. That's called photorespiration. C3 plants have photorespiration. C4 plants don't have appreciable photorespiration. Therefore, in C4s, they can scrub the CO2 down further than a C3 can. That's the reason for higher water use efficiency in C4 compared to C3. Now, let's get back. This is I mean, I don't mind spending some time because this is a really useful equation. It's approximately equal, right? There's other things to consider, but it's almost. And both these equations are useful. Okay, let's get back. The final precaution I want to talk about is called exclusion. What is that? Well, this part of the leaf is excluded from the increased pressure. The ideal case would be to have this right here at the top of this seal, at the top of this stopper, but even then there's going to be a pressure gradient through here. So part of the leaf, part of the thing that you're trying to measure, may have different water relations than the bulk of your sample. And so the more of your sample that you exclude from the chamber, the worse of a time you'll have making an accurate measurement. So here's an article from Annals of Botany looking at this. Here are water potentials measured in joules per kilogram. So remember, 1,000 joules per kilogram is a megapascal. And they looked at a pine needle and a wheat leaf. Both of them were 9 centimeters long. I don't know what kind of pine that was. Both 9 centimeters long. And they made water potential measurements on those needles or leaves. And here are the potentials, -1, -3 megapascals. And when they had, let's see, the pine needle, okay, the pine needle, when they had, okay, when they had a little bit of the end of the leaf sticking out of the chamber, they got this set of data. When they had a lot of the leaf sticking out of the chamber, they got this set of data. Here's the exclusion error, which is the difference from when they had practically nothing sticking out, as little as possible. You have to have some sticking out to be able to see it, but when they made that as small as possible, they got the best readings. As the water potentials got more negative, that excluded part, the more it was, the bigger their error was. Right? So that's their recommendation was, don't have much of the leaf sticking out there. 1 millimeter is all you need. That's another reason why, measuring a maize leaf, it's nice to have a big leaf and circle it a few times here in the chamber so that the part you exclude is a smaller fraction of that entire leaf. Okay, so in the extreme case, you can have anatomies that are just not amenable to pressure chamber measurements. So this paper by John Boyer, leaf water potentials measured with a pressure chamber, compared the water potential measured with a thermocouple psychrometer, what he calls the leaf water potential, and the water potential measured with a pressure chamber, which he calls the xylem water potential. And here's the one-to-one line. In most cases, well, with this Japanese yew and with sunflower, it's not perfect, but it's close. The two methods agree fairly well. But when he measured this rhododendron, I've got a picture on the next page, it didn't matter what the water potentials were. It never really was very good. Okay, maybe right there. How do you know that? Right? And this discrepancy in the measurements, they were never able to get rid of it by excluding more or less. It didn't matter. It was always there. They took a look at, or he took a look at the anatomy. Here's the plant that he used. Actually, I think we call that azalea. Yeah, azalea. Look, if you look at the anatomy of this woody stem that's sticking out the end of the chamber, there's this tissue in the middle called the pith, which is normally air-filled, spongy, air-filled space. As the pressure was increased in the chamber, and the water was being forced back up the xylem. Some of the water came from the xylem and infiltrated into that air-filled pit space. And then, the measurement didn't work, because that's not what the situation was when the sample was put off the plant in the first place. And they were never able to avoid it. So their recommendation is, don't use a pressure chamber to measure water potentials for nothing. More of a problem with woody species like this azalea than for soybean or cotton or any agronomic plants. So you can see there are differences in this table. And that's it. That's a pressure chamber. That's how it works. That's how to use it. And as I say, no class Thursday. What I'll do next Tuesday is continue talking about the pressure chamber and talk about how to make a pressure volume curve, and then how to interpret the data from the pressure volume curve to give us information about the water relations of needs and people. Okay, have a good weekend.